Hello.
Hello, everybody. I guess we'll get started. My name is Utkarsh Krishna. I am the secretary of the IEEE MTT SCV chapter. And on behalf of our chapter, I would like to welcome all of you to the April technical presentation. So a couple of housekeeping items to tackle first before we head into the technical presentation. Right now, the SCV chapter officers on the ballot, which, by the way, I think closes today. So if you have not had a chance to vote yet, please do so. So for the chair position, we have Jay Banwit. Vice chair, you have Utkarsh Krishna, that's me. Treasurer position, we have Tom McKay, and secretary, we have Mr. Than Tu. Once again, I think the ballot closes today. So if you haven't voted yet, please do so. Updates in response to the COVID-19 pandemic. Same as last time, all in-person meetings related to our chapter are canceled. Our monthly technical meetings, such as this one, and the officer meetings will continue in an online webinar format only until further notice. We are very active on LinkedIn, so the easiest way to kind of follow us if you're not an IEEE member or not an MTT member would be to follow the hashtag MTTSCV on LinkedIn. Once again, that's hashtag MTTSCV on LinkedIn. And of course, if you enjoy our talks and presentations, please support us by becoming a member. The links to join IEEE, if you're not an IEEE member, or if you're an IEEE member and would like to participate further, you can join the Microwave Theory and Techniques Society. The links for both are given here. Small request to attendees, please keep your microphones muted during the presentation, except of course while asking questions. We have a lot of people participating today, so this will help reduce background noise during the talk. So heading into the presentation, the title of which is Area Efficient High Performance Voltage Controlled Oscillators in Nanoscale CMOS. Our speaker today is Mr. Amit Jha of Renesas Electronics. So a small reminder to everybody, this meeting is being recorded. So the links to the video and the slides would be made available to all registrants. So within a week, you should see an email from me with links to video and slides. So short introduction to today's talk. A key component of RF systems is on-chip inductors, which occupy a significant portion of RF integrated circuits. As CMOS technology is scaled down, the percent area occupied by on-chip inductors has been increasing. On-chip inductors in typical foundry processes have low quality factor and usually are designed without space constraints to maximize quality factor because the inductor area scales with operating frequency, not with the minimum feature size of technology. For instance, it has been suggested that in 45 nanometer CMOS, an inductor for a 900 megahertz VCO occupies an area of a microcontroller core. So in this seminar, we will look at approaches to reduce area of high performance VCOs. The approaches will be verified by design of two VCOs operating at 4.3 to 5.6 gigahertz and 16 to 19 gigahertz with divide by 4 frequency divider in 65 nanometer digital process. So our speaker today is Dr. Amit Jha, who is a senior RF wireless engineer at Renesas Electronics, where he is developing millimeter wave and high-speed circuits for 5G and datacom/telecom applications. He received the Bachelor of Science, Master of Science, and PhD from the Indian Institute of Technology, Madras, Pennsylvania State University, University Park, and UT Dallas, respectively. From 2016 to 2017, he was with Jazz Semiconductor, developing IPs for front-end circuits for 5G applications. And before that, from 2007 to 10, he was a member of technical staff in Maxim Integrated Products, San Jose, where he developed compact models for nanoscale CMOS and LDMOS devices. He's a recipient of the Best Poster Award for VCO area reduction in nanoscale CMOS processes, which is quite related to today's talk, at SRC TXACE CE ICSS Circuits Review in 2014. His research interests include millimeter wave circuit design, frequency synthesis, and compact modeling of transistors. He's also the current chairman of the IEEE Santa Clara Valley Circuits and Systems Society, that's CAS-SCV, it's a sister society of ours, and he's also a senior member of IEEE. So with that, I'll hand it off to Amit. Amit, take it away.
Hello. Hey, hello, Utkarsh, can you hear me? Okay, I guess. So let me start. Yeah.
Yeah, we can hear you and we can see your screen now, Amit.
Okay, great. Okay, just to make sure. Okay, and okay. So hello everyone. Thank you for coming to this talk, and I'd like to thank Utkarsh for holding this event and for a nice introduction. The title of the talk today is Area Efficient High Performance Voltage Control Oscillators in Nanoscale CMOS. And as Utkarsh pointed out, I work at Renesas, but most of this work that I'm going to talk about today was done at the research group at Texas Analog Center of Excellence back at UT Dallas. So it's almost a crime not to talk about 5G before any talk. So, but in all reality, this topic is definitely related. Sometimes we try to make it related, but this topic is definitely related. But as you can imagine, 5G is all about connectivity with billions of transistors and devices. And the real unification of in all this broad scheme of things is the connectivity hardware. So you have this IoT, you have the transport system, automation, smart cities, virtual realities, medical services. So everywhere, the core thing over there, what you can think is the connectivity hardware. So sometimes you need hardware with high quality of connectivity where you have high data rates, or sometimes you just need devices which have intermittent connection, the ones which are like low power. So in terms of how are we doing to achieve this, because there is like a projection of like 50 billion devices or maybe more, depends on where you kind of research into which have you subscribed to, and people quote anything from 50 billion to even 100 billion devices in coming years. So to achieve that, definitely there's a lot of scaling that has happened in terms of interest to circuits and devices and transistors. And they've been scaling a lot. They've been following Moore's law, as you can imagine. We've been going beyond, like almost people are thinking of reaching 5 nanometer, 1 nanometer, and more than Moore's. You have all these other devices that are coming up: carbon nanotubes, ribbons, and then other faster stuff like I don't know. I mean, there's so much going on even in the optical space. There is so much of devices going on there as well. So, but the challenge has always been, of course, the device has been scaling, and you get very faster logic chips going on. But the problem is also the whole system scaling. Now, the thing that dominating is the whole thing is more of the pads, the I/O, all that passives that you talk about. So with respect to scaling, the system hasn't scaled that much. Of course, your core has become more strong. Your core has become more faster, smaller, but we're still far away from real scaling. So as I pointed out, with the scaling of CMOS technologies, you're getting more and more higher FT, higher Fmax, and that has allowed us to make really good compact and higher RF systems. So a look at the state of our transceivers would be now moving to our home ground of the RF world systems. We look at one is this is from the a famous Qualcomm's multi-band RF transceiver 8600 that was actually used in Apple 5, I think iPhone 5, and then Samsung S3 Galaxy phones. And you could see it's actually a multi-band. So of course you expect a big one, and you expect a big chip, and you expect a lot of inductors and transformers here. So you can see clearly a lot, like the whole chip has been a lot dominated by these passive components. And something relatively, the other aspect is like, for example, IoT, this work was presented in 2018 at ISSC this year, in 2018 from Tokyo Tech. And they show a low energy IoT Bluetooth operating at 2.4 gigahertz Bluetooth frequency, even though this is something different from the regular synthesizers. But you can still see that this whole chip is dominated by so many inductors. So there is definitely a process, or there's definitely a thought behind of scaling down the passives, or at least using the passives more in line with how we are scaling our devices and transistors. So the content, since we have a kind, I'm guessing we have a crowd with which has a big breadth in circuit and systems. And since we have already kind of covered all the buzzwords, and now I have all your interest now, what we can do is we can start with some inductor, some basics about the inductor. We're going to talk about the design aspects of the inductor. And we'll look briefly into what have we done in terms of the area consideration of inductor. And then we'll jump into LC tank design, which is important for the circuit that we're going to talk about. And again, think in terms of design as well as area considerations. How are we doing there? And then finally, taking all these concepts into the picture, we will design a couple of VCOs. It's no fun to make design twice, make the same mistake. No, what I mean is make the same success, but we will show the concepts that we are trying to make by successfully designing these chips. And then finally, we'll conclude this talk with kind of steps for the area efficient VCO, put a recipe, and hopefully those will be the points that we can take out from this talk. So let's begin with inductor. So inductor research was actually a very prominent form of research in late 90s and 2000s. And this is why, because you see this chip from ISSC 1995, and you see that like 4 bond wires, right? And these bond wires are like they are definitely high Q, so that's good, but they're expensive, they're costly. Then there's a problem with the system integration, right? There's a problem with the modeling, and then in between the interaction, and then you obviously have limited choices. So definitely inductors are needed. Inductors have like little DC voltage drop. You could resonate out transistor parasitics. You can extend the bandwidth, and then of course the favorite circuits that RF circuit designers use, LNA, VCOs, mixers, they use a lot of inductors. So around so the points I just said, and so around the time of 19s, like 25 years from now, 30 years from now, a lot of work started developing on-chip inductors. So the on-chip inductors were very cool that you could put them in the chip itself and kind of reduce the cost. So the cost was the one factor. And then of course, once you started designing them, started kind of exploring them, and then there was this surge of a lot of good publications, a lot of good research from everywhere. People caught on to the idea that we could use on-chip inductors for most all of the RF work. And so we had this different shapes of the inductors. So over here, I show you rectangular, circular, octagonal, symmetric. There's a stacked, grounded shield, parallel spirals. And you would have probably seen one of these inductors, and you probably use a combination of these two or whatever. So now it's become very common. But the key thing obviously is what we talk is the quality factor, right? The quality factor, how do we optimize it? And in one true sense, it's probably for any RF guy, it's RFIC guy, it's one of the challenging things to get into before they start exploring the RF world. So, and one quick point over here is just for anyone who's just going to start on the inductors is obviously you use inductors because, as I said about, it's obviously on system, on chip, but when you start using the spiral inductors, what you do is you get more mutual coupling between every turns. So you get more larger inductors than a straight wire. And the mutual coupling is, of course, between the wires are positive. And then so but then the thing with the on-chip inductors is more than that. There's a lot more going on in terms of we have to be careful over the loss mechanisms that are happening in the spiral inductors. So the first thing obviously is the resistance itself. So right, so when you design a spiral inductor, there's so much of DC metal resistance that comes up. So a good idea would be to draw on a thick metal layer where the sheet resistance is low. You could also shunt the metal layers if you are kind of designing a digital CMOS where there are very thin metal layers. You can kind of shunt them together and have a thick layer. Almost these days, every foundry offers copper metal layers. That'll be great to use. And then, of course, you have to be careful about the underpass, the metal MVGs that you use, and they're highly resistive. So you have to make sure you design them carefully to reduce your losses. Then another effect you obviously have is the skin effect that kind of happens at high frequency. As you can see from the picture here, when you go to the high frequency, almost all the current flows at the surface. So the current in the center of the conductor is canceled by the eddy current generated by the changing magnetic field that resulting from the alternating current. So the current starts crowding at the edges and increases the resistance. So as I said, one of the big kind of step becoming RFIC is understanding these spiral inductors. And then, of course, there are other things like capacitive coupling that happens. As you can see, because of the changing magnetic field here, because you have the voltage at each point at the spiral rise will rise and fall with the time, and that causing displacement current between the substrate and the metal. And so there will be this current that will cause and reduce the Q of the inductor. There's also a magnetic coupling that happens to substrate, and this is kind of interesting. That comes from the Lenz's law. For example, you have this current that is going this way, and then the current is induced exactly opposite way on the substrate. And you could model this as kind of a transformer. And then in this transformer, you could do some modeling. And definitely what it does is, because of this, what we call this eddy current, and because of this eddy current, it reduces your inductance of the coil or of the inductor. So there has been a lot of work, as I said. There's some really good papers. There's one good paper from the design of RF spiral inductors from Burghardt's. And they suggested a very a model, which is kind of, it's still not complete, I would say, because you see that there's an RS, which is frequency dependent. There's a frequency dependent resistance of the inductor. But as you know, it depends upon the frequency. So, and it seems that it's a constant. So obviously there's a broadband model, which has a frequency effect, which takes care of the frequency effect, which is again a lot in papers, which is all published very well. Then you have this, and then this model can also shows you that how eddy currents are kind of put over here in LE minus M. And so they try to put all the R sub, R shale, the high frequency effects coming from the COX and RB, the coupling to the substrate. So this was one of the, I think, a good paper kind of introduced to you all the losses that can happen in the spiral inductor. And then this model actually, it's fair to say one of the models that came from Patrick Yu's paper from Stanford was kind of simplifying and kind of putting together all the things. So the CS is again capacitance between the turns of the inductors. Then you have the inductance, you have the RS, COX, and COX is with the capacitance between the substrate and the coil. And then of course you have the substrate resistance and the capacitance itself. Again, as I said, it's more of a narrowband model. So for the broadband model, you'll have to, of course, use other models which are more complex. So another important thing about is the Q of the inductors. The Q of the inductors are kind of very, it seems straightforward. Like the conventional Qs, if you use, there's something called conventional Qs, and it is kind of difference between the magnetic energy and electric energy, and that comes from because you think you have the inductor and you have the capacitance, and then they resonate out. So at low frequency, you have more magnetic energy, less electric energy, and so this works okay until you hit the resonance point. Once the resonance point, the Q becomes 0, as you can see in one of these plots over here, right? So obviously this is not, doesn't make sense. So what we do is we have there's a very good paper actually from my advisor where he talks about the Q factors of the inductors, and the bandwidth Q comes from there. Over here, bandwidth Q basically it shows it comes from the fundamental definition of how much energy you have stored in that passive element. So in this case, it's an inductor, so you have magnetic energy, and essentially what it means is it's the ratio between the frequency, that frequency, and the bandwidth at that frequency. Now you might ask how you get the bandwidth at frequency. So what we do is we add a numerical capacitance, and that can resonate out an ideal capacitance that can resonate out the inductor, and from there you can get the bandwidth of that at that particular frequency. So, and of course, in this one, there's another one is called phase stability. Phase stability is very much similar. It measures the kind of the variation in the phase at that frequency. So I didn't go much into it, but if you look at this paper, you can get the definition. So most of the stuff, the results I'll be showing, I'm going to talk about bandwidth Q rather than conventional Q, though I'll probably talk about conventional Q as well. So now the inductors, as I said, has this problem with the capacitive coupling. So how can we solve that? So there was again a paper from Patrick Yu that came with the with the inductors with the ground shield. So what happens is, because as I said, there's a displacement current that goes from the inductor that's coupled to the substrate. So what you put is, if you put a shield, as you can see over here, it allows a low resistance path that the displacement current can flow into the to the substrate. Now, if you put a solid conductive ground shield, right, as you'll see that there's kind of a spacings here in the shield over here, and that is there for a reason, because if you put a solid conductive shield, as if you remember back from our Lenz's law, you was going to get an image current which will exactly oppose the current on this inductor. So you definitely want to have this loop that is shown over here, right? So what we do is we kind of break these this shield, and we call this pattern ground shield. So this reduces the capacitive coupling, and as well as there's no eddy current that is being, as well as breaks any eddy current that might be there because of the shield. But you must remember that there's still eddy current that is actually flowing in the substrate. Okay. So based on this, there's a very simple, again done from one of papers from my group, was if you take a simple inductor model and you kind of change your R sub, simplify it, go all the way from like all the way from short to the all the way to the high. What you see is when the R sub goes to infinity, the current through R sub actually becomes 0. So the power dissipation in the substrate is actually 0, and the Q is high. So that will account for when you have high resistive substrate, right? But then if you go the other way around, if you can make the R sub equal to 0 almost, then the power dissipation R sub again becomes 0 and Q is increased. So typically we do not, if you want to make it R sub very high, you have to deal with the process. You have to deal with the fabrication, which we don't have much control. But what we definitely have control is you can put a pattern ground shield and be somewhere in this region and get higher Q. So now, how are we doing in terms of area? So of course, the first thing is, as anyone would say, is a lot of it is not in our hands, right? Because the back end actually comes from the fab, all the fab from the silicon processing guys. And if you definitely have a very good metal stack, with like thick metals over here, multiple metals, far away from substrate so that you don't have much coupling, and you can actually make really good inductors at the top using the top metal layers and get a good Q. And you can obviously make it smaller or make it sizer as per your needs, right? The second thing is you can as you can imagine, there were people who used to use single-ended inductors over here. So single-ended inductors, for example, if in this differential circuit, as you can see, it's taking too much area. Now, what if you combine this and make it a center tap symmetric inductor, right? And now in this one, you've combined this together, and now because the area is almost kind of halved, you have much less coupling to the substrate, and so your Q goes higher. So you get more Q than this thing. And again, you've saved a lot of area. Another quick point to be noted over here is, obviously, you can see around here, this line over here, the magnetic field actually cancels out if you do. But in this case, the magnetic field is strongest over here. So there is some advantage to that, but other than that, I don't think there's a big advantage. So on the stack inductor, there's some research again done by Razavi. He published a few papers on the stack inductor, and the thing with the stack inductor is it's good that you can put these inductors stacked one to another, and it actually goes by n square theoretically, but again, the capacitance starts kind of hurting it, and actually cannot get higher than maybe 4 to 5 gigahertz. So, and then again, so the Q hurts, and if you don't have a very a good metal stack, if you can get these two at the top over here, maybe you can have a good Q. But other than that, this kind of usually doesn't work. So far, we kind of covered all about the inductors, how we can optimize inductor. Now, the thing is, it's not just the inductor, but the LC tank, which is the core of this kind of a VCO circuit. So I show you here the NMOS cross-coupled LC VCO, and then as you can see, the phase noise of this VCO is actually decided. One of the biggest factor decided by this is Q factor, and this is the Q of it's the Q of the loaded tank, and you can see it depends upon Q square. So if you kind of make it Q like half, you'll lose your phase noise by 6 dB. So the Q factor is definitely the most important. There are other factors as well, and these are more like fitting parameters, and of course there are much more nicer phase noise models, which give you more in-depth analysis of the VCO. But at least from this model, we can definitely say the thing about that Q is indeed a big factor in deciding the phase noise of the VCO. So a typical tank would be you have L. I've converted this L to a parallel resistance RP1, and then you have this capacitance or a varactor. Varactor means a changing capacitance. And as you can see, the resonator Q is given by 1 over Q. It's a reciprocal of like 1 over QL, 1 over QC. And so the tank Q depends on the Q of the both, of the inductor Q and the varactor Q as well. So before we actually jump more into it, I will briefly give you what is the varactors that we're using. The varactors that we'll be using are the accumulation mode MOS reactors, which are actually NMOS inside uh, an N well. So the variation of the capacitance with the VGS, I think there is a, okay, we will take the questions at the end, I think. So the accumulation mode MOS reactors, as I said, they are like NMOS placed in N well. And then you have this model of the of the MOS reactor. Usually we can't do much about, as a designer, you can't do much about what's going on inside this reactor. But what you can definitely do is a good layout to reduce your gate resistance so that your Q is high. Typically, your CM into CMAX, as you can see, it changes from VGS as you change your gate bias. This Q shows a kind of a drastic change, but actually it doesn't. In my practice, what I see is Q drops as we increase cap from C min to C max, because the relative rise in capacitance is actually greater than the fall in the resistance. So if you do a narrowband approximation, you would see that actually the Q doesn't. It actually drops. So now let's talk about the tank design. So what we're going to do is we will design inductors and reactors required for VCOs operating at various frequencies at 5, 10, 20, 30, and 40 gigahertz. So as we know, loaded resonator will have parasitics from the cross-coupled transistors, but they're here ignored here for the simplicity. And the Q factors are actually the ones that we get from the PDKs. And the Q factors for design of the inductors are actually simulated using the HFSs that we used to use that time. For each resonant frequency, what we did for the inductor itself, because it's the area is going to get dominated by inductor, we designed for the maximum Q factor by changing the diameter of the inductor. These are all octagonal inductors. The number of turns, the trace width, and the spacing. Okay, and at each frequency, we are not thinking about what ADA it takes. We just design it for the best possible Q. So based on that, as you can see now, is like at every frequency we have an inductance. We have the and then it also shows you the area. Actually, it's the area of the inductor, but as it's mostly decided by the area of the inductor. And you can see the Q of the inductor. It actually starts rising because to the first order, it starts increasing with the frequency. But again, the other high frequency effects start coming up, so it starts going down. The Q of the reactor is actually starts as you go high in the frequency, it stops dropping, right? So there is a sweet spot where you get maximum Q of the resonator. And for this process, it's like around 20 gigahertz. So again, few things that this gives us is like is that you can definitely go much smaller area, like around 40 gigahertz, you will have an inductor which is like 12 times smaller than this, but your Q has gone down almost like half, right? So there's a certain pay that you have to there is a certain penalty that you have to pay to go to the high frequency sorry, there's a certain penalty that you have to pay if you have to reduce the area of your a tank. So based on this, we design our first VCO. The first VCO that we design is the one that we take, the top one at 5 gigahertz. We design with these this LC tank. So we design, then we'll talk about the layout, we'll talk about the resonators, and then we'll finally see the measurements. So so this was the a simple NMOS cross-coupled LC VCO with buffers and bypass caps. It's almost a textbook VCO. You have the PMOS current source transistor over here that is biasing it, and you have the the bypass capacitors. I'll talk about that in a minute more. The thing to reduce area is we use inverters over here as a buffer. And again, we use 5-turn, I already mentioned about that, a 2 nanohenry inductor. And in this case, it's a digital process. So I think it was a 7 metal or 8 metal process. I don't remember very well. And then we shunted all of them together and we got a reasonable Q by standards of CMOS process, around 8. And the size of the inductor is about 120 micron by 120 micron. So as I said, we're going to talk a little bit about the bypass capacitors. So bypass capacitors, again, definitely want higher Q. Q of the MOS capacitor must be high. Typically, you can get about 8 to 10 Q in the usual foundries. But one important thing about designing these bypass MOS capacitors is, if you just take one long finger and if you calculate the on resistance, okay, there's a chat. Okay, so yeah, there's a couple of questions from Vinita. I'm going to respond them in the later. Okay, this is about usual NMOS VC and PMOS VC and LC oscillator. So the MOS capacitors realized. Oh, sorry. So if you look at the on resistance of this MOS capacitor for one long finger, it can be huge. But what you do is, if you kind of make it a multiple short fingers, then you kind of reduce this on resistance from to the order of n. And remember, this divided by n, and then since these are in parallel, you'll actually get the decrease r on by n square. So this is very good, and this is something we're going to use it to our advantage. So using this as an advantage, what we do is we design this VCO, and as you can see, what we have done is we've kind of tried to put all the components that we talked about: the PMOS current source, the cross-coupled transistor, which was the amplifier, the inverter buffer, the MOSFET actor, the bypass caps, everything underneath it. And how do you do it? So what we do is we try to put everything inside the inductor so that they can act like a pattern ground shield, right? So the polysilicon gate fingers of the PMOS current source, the top plates of the MOS bypass capacitors, and the metal connection for the bottom plates of MOS capacitors, they're all used to form pattern ground shield. Okay, so we try to put them as much perpendicular to the direction of the inductor current flow, but obviously this is not possible. So, but as you can clearly see, placing them as a multi-finger kind of acts like a pattern ground shield, right? So, so this breaks the eddy current flow in the ground shield, as I said about, and that reduces the current and reduces the loss. So, but what you have to do, what we have to be careful about is, when I show all this current flow is, as you can see, these current flow are that the ground current and the bypass capacitors, that can be, there can be loops over here, right? As you can see, this is kind of a loop over here, correct? So what happens is, with many components and connections underneath an inductor, there are numerous opportunities for all these loops to be that can be there, that can allow the flow. For example, you can see there's a loop 1, and because you kind of split your yeah, there's a camera on of someone. Okay, because of the splitting of these capacitors, what you can see is, because you're going to design in a VCO with symmetrical halves, so you have this bypass caps which are kind of split exactly half, right? So now you can have a AC current flow that's going to flow on this loop 1. You can have this loop 2, loop 3, loop 4, loop 5, and these are the ones that we identified. There could be as more loops as well, but so Yes, as I said, there's a question from Q. Will change when you put component between the coil, right? Yes, that's what we're going to talk about more as we go on. So as you can see, there are kind of like five. We are showing you five such kind of loops, right? So loop one is an AC ground loop, which includes the current source, drain, bypass cap, and the loop is, and how do you kind of, and then and I, and as you can see in the layout, it looks something like this, right? So how do you kind of break these loops? So one quick way, something very simple is, when you have the split between these two over here, just do not connect one of these guys, right? If you can have two separate VDDs, that's great. But if you do not have, then put it there, but do not connect them, right? So for these one, we did the same. For this one as well, we kind of we did not connect one of these. We kind of broke the connection over here. And for this one, for this VDD, actually for our chip that we had the two different we had two separate pads. So we kind of connected to two separate pads. So there was actually no AC loop being formed there. But for these two, where the resistors were there, we had to come up. We came up with something else as well. So example over here, what we did was, for example, the resistor is over here and you have the bypass caps. In the normal situation, you would have something like this. So what you can do is you can make this resistance as a part of this cap over here, right? And this will kind of effectively break your loop. There is obviously a trade-off here because this V-tune node, before you had this low pass filter that was coming up in this case, and that was kind of cleaning up a lot of this noise that can come up over here on the V-tune node. But in our a lot of the measurements that we did, we used battery, and again, this is going to be used in a VC in a PLL, and you can design your loop filter that can be suitably designed to reduce such effect. So, of course, we need to understand how these loops affect the inductor performance, right? So what we do is we take the structures underneath. So what we do is we take we put all the component. We take the GDS. We kind of design this, as I talked about. We take this whole VCO and we kind of import it to our from the cadence. We get the GDS out. We put in the HFSS. Obviously you'll have to make sure that you kind of model the diffusion regions for the bypass caps, the varactors and active devices using the foundry, whatever the values they've given you, the resistance and everything. And then what you see is that if you kept the loops, if you did not eliminate the loops, you would see a kind of like a 23% in the degradation of the inductance itself, right? And you see a Corey factor being degraded by almost 26%. So it's important that if you're going to design components underneath the inductor, these loops need to be removed. Okay. I can also talk, I understand if you kind of do the simulations with all the components underneath it, it's going to be a mess. So you might get convergence issues and all that. So there are some tricks that you can use. You can kind of combine all those vias together. And there are these via bars you could use. And so definitely there is a learning phase in how you can kind of make these simulations. At that time when I used to do it, used to take a long time. I'm hoping the simulators have become much faster now. So, but you still probably have to kind of combine metals and vias together so that you can get this fast. You can get the simulations done faster. So based on this, we design resonator test structures because we want to definitely evaluate the effects of placing the components underneath the inductor. The two resonators were fabricated as shown here. So obviously what we do is we take the same circuit, ground everything, and then we just take it out the outputs from over here, right? So what we do is and then again, as you can see that there's one resonator with everything inside, one resonator with everything outside, and we measure the Q, the bandwidth Q, and what you can see is it's almost like 15% higher. And in fact, if you kind of review a lot of papers on the pattern ground shell, how much it improves the Q, in the paper that I talked about, for example, from Dr. Patrick Hughes. Actually, he's professor at Hong Kong University now. So Professor Hughes' paper, he also kind of sees like 10 to 15% improvement in the pattern ground shell from the Q, using the pattern ground shell in the Q of the inductor. And again, other papers. So you get about 10 to 15% higher Q. And we see the same over here. So the MOS bypass capacitors, as I said, they're the largest components, almost 50% area. And for our case as well, it was Q of 10. And because of this and the other structures, we could form a kind of a pattern ground shield. And we got like a 5.5, 15% higher than the inductor. Notice that the Q of the inductor was about 8, but of course with the adding it's a loaded Q, right? So it's with all the parasitics of of the circuit. So from the measurements wise, now we come to we design the VCO. Again, the one VCO is 120 by 120, other VCO is 240 by 180, 185. And as you can see, I put the phase noise plots here. The phase noise plots is about like minus 117. I think we got a little bit better on the VCO in. I must confess that at that time, I was not the smartest one to do a lot of good measurements. So probably I would have done much better now. But again, those don't look that bad. And then if you sweep around, if I go from 4.4 to 5.6 gigahertz all the way, you can see that the phase noise of actually the VCO in is a little bit better than the VCO out. And both of them achieve a good tuning range, 26% tuning range, and within the good 4 milliwatts of power. So how does this work so far compares to the state of the art that we have? State of the art in which people put, actually some of the people have tried this, right? So there was some work from Columbia, from Dr. Kingett's group with Dr. Zhang, and that they kind of, they showed a VCO in which they just put the varactors and cross-coupled pair, the amplifier, underneath the inductor. And they show reasonable performance, actually very good performance. But again, the big thing is they still didn't have the big bypass caps, the buffer, other devices were all outside the inductor, right? And again, as you can see, they put these devices just like us in underneath the coil, not exactly in the middle, right? And then, and then there was another guys from, I think from Japan, again from Tokyo Institute of Technology, is that they started doing these work in which they made like extremely tiny VCO cores, like 27 micron by I think 22 micron. They put something over there. I don't know exactly what they put. Maybe they just put the cross-coupled pair, I think, and probably were actors. But then everything else was outside. So as you can see, the other stuff that is used for the VCO, the other components, is actually much bigger than the VCO core itself. So then there was another attempt from Columbia, again from the same group. What they did was they put underneath the inductor, they put the loop filter part of your MOS cap. Usually what you do is you try not to put MOS caps for your loop filter, because again, they increase the FM noise and decrease linearity, and MOM caps are preferred. But again, definitely because of the parasitic capacitance between the inductor and the MOM cap, you probably wouldn't like to put them underneath the inductor. So based on this, so what we have done is, again, this work we put, it's much smaller than the work defined. And again, it's partly because the technology we've been getting better, of course, but we kind of also put everything, scale everything to put everything inside the inductor. So as you can clearly see, we achieved, there is of course two figure of merits that's usually defined for the VCO work. There's an FOMA, then there's FOMTA. And in the FOMA, you also kind of normalize with reference to area. And at that time when we published this, I think this published in 2014 in RFIC, we had the highest, for example, of course, the FOMA of the guys from Japan is definitely much higher. It's around minus 210. But again, I don't know if you can use this VCO with a phase noise of minus 93 dBc per hertz at 1 megahertz offset at 9.9 gigahertz. So for the high applications that need higher, lower phase noise, definitely this can be counted. So what we were able to achieve, and then if you include FOMTA, and of course they didn't have very good Q at all, and they didn't have good tuning range at all, because they had to make everything so small, is that their FOMTA was about minus 506. So a clear thing of what we have done over here is, and a clear understanding is, you cannot make it small. You have to make it big enough so that you can put everything underneath it so that you can get this performance that you want, right? So you want to design an inductor, but you cannot make it just so small just to get lowest area possible. So the conclusion that we made so far is, you would design an inductor, you increase the number, you try to put as many components underneath the inductor so that it's huge. There's no compromising on the Q of the inductor itself. There's no compromising on the design of the inductor. And you can put all the bypass caps and other components to form the pattern ground shield. And you can improve the Q and reduce power consumption, of course, because you have better Q now. So, and this is how this so far, so until this, that's what we learned, that instead of kind of making it smaller and smaller and not getting anything, the idea is to make it big enough so that you can put everything underneath it and work around to make it act like a pattern ground shield. But we can still do something more, because now we said that we still haven't optimized our Q of the tank, right? So for any process, we know that there is a frequency at which the Q of the whole tank or the resonator is maximum. So for our process, it was about 20 gigahertz, and you could see that you had almost gone 1/3 of the area, and you got very high, probably the best Q. So based on that, what we did was we again rolled our sleeves and designed the new VCO, which is about 16.2 to 19.6 gigahertz VCO. So again, the same design, layout, resonators, measurements we'll go through. And also we wanted to compare this to our previous work. So what we do is we design thing, and we put a frequency divider by 4, and we get back from 4 to 4.9 gigahertz frequency source. So now, given our first success with the chip, with this one, we went a little bit more. We wanted to use a little different topology. So what we did was, we used this time an NMOS, PMOS cross-coupled LC-VCO with buffers and bypass capacitors, right? So in this case, what we have is, when you use the NMOS, PMOS, the good thing about NMOS, PMOS is that you can achieve twice peak differential output amplitude than the NMOS only or the PMOS only. And this, of course, leads to better phase noise. And it's also because now you have 2 amplifiers running for you. There's also kind of more power efficient design as well. And then the only penalty that you get is, since you're using more cross-coupled amplifiers, your tuning gain is going to go down, right? There's also a lot more work on how the output oscillation waveform has a better, rise and fall symmetry, so you get much better 1 over F kind of up conversion. Like your corner also of the 1 over F noise is much better. You have much lower phase noise even in that regard as well. So okay, so these are the same points I just said now. So based on this, and then of course we also have the divide by 4, as I said. The divide by 4 is a typical current mode logic divide by 2. It's so what we do is, we want to make them, again, for our purposes, we want to make them as small as possible. So obviously the first thing is we remove the current sources. There's no current sources here to reduce the area, and as well as get more headroom for your circuits. You also want to optimize it as much as you can so that you can reduce the area. So for example, in this case, The cross-coupled transistors can be designed much smaller than these differential transistors for the first one, and then this one, and then you have obviously two divided. There are two more stages. And the other one is actually can even design you can actually even make it smaller. So this is all done to reduce your size. So again, the layout, and in this layout, as I said, we kind of went a little bit more in depth, like, because as I said already, that we expect a lot more the strength of the field to be maximum over here. But we thought now we actually don't have space, right? Because now we have 70 micro by 70 micro inductor, and we do not have just space to put just underneath the windings, just over underneath here. So in this case, obviously everything also scales down. So even the bypass caps are now scaled down, and everything is scaled down. And now we have tried to put everything within 4,900 micron square area of the VCO. So again, these are the components that will be put over here, just a list. Also in this case, we had a choice of inductor leads. Now what so happens is, if you want to make a more compact choice, in this case, what we had this luxury, actually we sort of looked at it, how to put it. And in this way, you can see that instead of when you put the circuits underneath the inductor, there's a much better facilitating, there's a much better way to put the leads from inside the the inner turn of the inductor. So this obviously has much less. This kind of reduces your parasitics. You have much less shorter routing. For the one that is outside, again, you use the outside leads. So obviously, because of this, there's a little bit of difference in the inductance, but not so much. But as you can see here, there's a little bit of inductance difference, but then of course your Q is also much better because you have kind of reduced parasitics as well. So again, just like the previous effort, we designed the resonators as well. So you have the test structures. So you design your VCO. So we actually did three test structures. So the first one was the VCO with divide by 4 underneath the inductor. Then there was another one in which you design the VCO underneath the inductor, and you put the divider outside. And the last one is you put everything outside the inductor. And what we notice is that the VCO under the inductor with the divider outside the inductor was actually pretty much same as the divide by 4 with everything underneath the inductor. So from now on, we'll just kind of talk about two, like everything inside the inductor and everything outside the inductor. So to measure the resonator, obviously, as I said, the leads are inside. So what you have to do is you have to put an underpass, right? So there's this underpass that needs to go from the inside to outside. Even though we kind of optimize it as we can, it still adds some parasitics to it. So this is the again the QBW, as you can see. So again, 15% higher than the one in which the resonator is all outside. This could actually be even much higher, given that given that we have this underpass that I just talked about. Now, so we did the VCO measurements. So the two VCOs over here, I don't have the chip photograph just for the VCO itself. So the VCO, you have 70 by 70 microns, a very tiny VCO, and then one is 70 by 140. You just put everything outside. And then you can clearly see that the VCO in is actually almost more than a 1 dB better at 1 megahertz. In fact, it's actually much better at 600 kilohertz, the phase noise. Power-wise, they actually, the VCO instance has a better Q, actually burns less power. The VCO out actually burns a little bit more power. The tuning range is almost close to like 19%, 18% here. And you can clearly see that the VCO 20 gigahertz in is actually outperforming the one at the outside. So that was just the VCO. And now we, obviously, as I said, we need our 4 gigahertz signal back as well, right? 4 to 5 gigahertz signal back as well. So what we do is we put the divider and we put the buffer for the divider as well, the common drain buffer. Let me also remind you one thing that I think some of you might have noticed here is you probably saw this bypass cap outside of it. This bypass cap outside is actually for the drain, common drain bypass cap for the last stage buffer, which you actually might not need it. It's just for the measurement. So the VCO we divide by 4, again, as I said, since we measured three resonators, similarly, there were 3 divide, similarly, there were the VCOs, as I said, there were 3, everything, all of them inside, and then VCO inside, they were outside, and then all of them outside, right? As I said again, the VCO inside and with the divider outside, or the VCO, everything inside, they were pretty much similar in the performance. So we're going to just compare everything outside and everything inside. Again, the buffer for the VCO and the frequency divider circuits, I think we spent a lot of time trying to optimize them, and they only burn about 1.6 milliwatt of power at 1.1 volt PTD. So now the time for the measurement. So this is the chip that we have, the VCO 20 gigahertz with the divider, it's 70 by 70, and again with the outside 70 by 140. And as you can see, there is a VCO divider in, and everything inside has a much better phase noise compared to the one outside. There is a little bit, as you can see, we have a much better, it's almost like a 2 dB, 2.5 dB better over here phase noise. There's a little bit more better phase noise over here, and that we don't clearly understand very well. That might be filtering because might be some filtering, inherent filtering because of the way we have laid out the structure. It's also because we have the we use a spectrum analyzer in which there's a lot of drift as well. So it's very hard to say something about this frequency at lower offset frequencies. But definitely much better performance. And obviously to make sure that it's just not one chip, what it was, we measured for 4 chips, and we consistently saw that the performance of the VCO and the divider inside the inductor was actually much better than the one outside the inductor. And also want to make sure that the frequency divided by 4 does not kind of kind of does not change the output power. So what we do is also we measure the power at subharmonic frequencies of VCO, and we see that it's pretty much consistent with what we have. So now in the comparison table, once we have all this so much these VCOs, now we can compare to not just the work that I just showed. This is from the Columbia from 2006, and then from the other from the Tokyo, where they kind of really made it small. But you can also compare it to the newest and the greatest VCOs that have come on in the RFIC and ISSC. And you can see that the 16.2 gigahertz VCO underneath it, if you compare the FOMA and FOMTA, is actually much higher than the rest of the ones that has been published. Some of the areas have been kind of extracted from the paper. Also, one thing to notice is, even though this is the core area, I've not included the area of the buffer and the bypass caps. And as you might have seen, they take a lot of areas, right? So obviously, these area-wise, these VCUs are efficient in that way. So now with that, let's see. Finally, we kind of come to the how do you design? So let's kind of conclude this. Like what are the steps? I think I'm almost out of time as well. Conclude how much. What are the steps that we can design such VCOs? So obviously, the first step would be select the inductor with maximum Q at the frequency operation to achieve the specs that you have, the phase noise, swing, power consumption, right? And the inductor must be designed without AI constraint. Get the best Q possible for your inductor, right? And so that you can add as many components as possible underneath it. Obviously, for a CMOS process, there is a certain frequency where the time Q is maximum. This allows more area savings. A divider may be needed to reach frequency of interest, and you would need a lot of EM simulations, as I said, to optimize the tank design. Now lay out all the bypass caps, all the components, passive components as multi-finger structures to form the quasi-pattern ground shield that that we just described. And that will reduce the substrate loss and improve the inductor Q. We spent quite a bit of time how to understand how to minimize the AC loops. So this is a definitely important part of the design, that you have to reduce the AC loops underneath the inductor to avoid the degradation. And again, sometimes depending on the turns of the inductor, if you have the actually even turns, you probably might have your leads inside at the inner turn, right? If you have even number of turns. So the differential layers of the inductor might be on the inner turns to reduce parasitics. You have to model all the regions you get from the PDQ of the foundry. You have to get the exact resistivity for the bypass caps, varactors, and active devices for your EM simulation. To reduce the time of simulation convergence errors, as I said, you should kind of get all the multi-vias, get together, combine them together. And even for a lot of metals, you might have small metals everywhere, kind of grab them together and make it one piece. And similar to the VCO with the EM model, finally you get an S parameter model. You might use, actually, these days I use a lot of EMX. You can use EMX and you get an S parameter file. And you can use it with your components underneath to fine tune the design. With this, I thank you for everyone. I will take questions. And then of course, if you're out of time and if we can obviously discuss more, you can definitely reach out to me on this email address, and I'll be happy to talk more about it. So with this, we can look at some of the questions that we saw. Chat. Okay. So this is the. Let me ask Utkarsh, how much time? Hi Utkarsh, how much time do we have? Do I have?
We can spend about 5 minutes, maybe. We are actually already over time, but
Okay.
It's fine. So maybe about 5 minutes or maybe a little bit more.
Okay, all right. Thanks, Utkarsh. So Yasha is asking that Q will change when you put component below the conductor, right? How much it changes below how much does the Q changes with the components below the coil? So obviously I talked about how you can, if you just put the components underneath it without any kind of layout strategy, try to make it try to not make it like a pattern ground shield, your Q will degrade. But if you kind of take all the possible steps that I talked about, you probably get a higher Q than just using the inductor itself. Then Vinita asks me how do you want to choose between NMOS VCO or PMOS VCO in LC oscillator? Is it noise versus speed trade-off? Even though this was not the topic of this talk is, yes, of course, you have to kind of, usually the PMOS are slower than NMOS, so usually NMOS VCOs, there was a time when PMOS VCO used to be outperforming in terms of the noise. It doesn't seem anymore. So it's again, it depends on the foundry, so you should definitely characterize each device and see which one is better. Vinita again asks, which is the correct metal level to put a pattern shield, or how far from the spiral inductor should the pattern shield be? So we are not using metal level, as I said. What we are using is we are using the poly silicon of all the bypass caps. We obviously have metal 1 on the bottom, and then we have, so most of them is right now is the poly silicon and the M1 and the components that we are using. So we are not using, actually you are not using any other metals just for the pattern ground shield. So okay, thank you, Tam. Thank you, Tam.
Hello,
Yes.
Amit.
Yes.
Hello. This is Paul Khanna.
Hi, Paul.
I have a question regarding your measurement of the loaded Q.
Sure.
When the loaded Q is so low, like you are showing some measurements where the loaded Q is like maybe 1 or 2,
Yes.
and measuring those is, what do you use? Is it basically the 3 dB bandwidth you take, or I mean that will be very tough to do measurements when your Q is 1/2 for the loaded Q.
So I mean, we get about 6, 7. So definitely.
But the measurements are going down to 1/2 on the left hand side.
Are you talking about this? Oh, wait.
Yeah, it came by
Yeah.
here.
So
Yeah.
sure. So this one.
Yeah. The
Oh, yes.
measurement on the left hand side, like at lower frequency.
Yes. So exactly. So the Q bandwidth, what we did is that you add a numerical capacitor, and then you get, and then you kind of resonate it out at that particular frequency, and then you measure. So what we do is first we go and measure it, and then of course you kind of de-embed all the losses, right? And then once you get it, then we have this MATLAB script. You kind of run the MATLAB script, adding a very numerical capacitor, resonate it out at every frequency, calculate the 3 dB bandwidth there, and then you kind of get the QBW from there.
Okay, so you are not measuring 3 dB bandwidth.
No, we are not measuring 3 dB bandwidth. We are
okay.
Just, yes.
Thanks.
Sure.
Yeah, hi Amit. This is Adil from India.
Oh, hi Adil, how are you?
Oh my.
Yeah, yeah. So yeah, first of all, like thank you very much for this excellent talk, and it was quite interesting. I have not worked on VCOs itself, but yeah, it kept me engaged in the entire presentation. So
Sure.
one basic question on inductor, like you in the initial part of your presentation, you showed like we can make inductor. No, I don't want to go on slide.
Okay.
It's a basic question, like from like circular inductor to octagonal inductor, or for rectangular inductor. Like, what are the basic difference in terms of fabrication or performance? Like, I have seen using octagonal inductors.
So yes, so those inductors, I mean, I've taken from, I think from Razavi's book. So basically, it's these days everybody uses octagonal inductor, right? Because octagonal inductor is the best optimum for the area, the Q, and everything. Okay, and obviously the ease of fabrication. So before that, people used to use these, what do you call it? Before that, people used to use all these rectangular ones. Rectangular ones, obviously you have these kind of a sharp ends which increase the resistance. So you kind of this. So these days, I don't think anybody uses rectangular. Most of them, everybody has gone towards the octagonal inductors.
Yeah, even I have seen like using octagonal only. I have not worked on inductors itself. I'm like working on high speed data converters. So yeah, so I was curious to know about is there any difference in terms of fabrication or performance, and that's I think you have cleared that. And yeah, all right.
Yeah, I mean there are certain scripts that you could write. You can actually write in to design, because the circulars apparently have some problems, because you have to have all that 45-degree lines for in terms of designing it. But octagonals are the kind of the best of the both worlds. So there's a question from Yasha. Thank you, Adil.
Yeah, thanks, Amit.
Sure. There's a question from Yasha. Did you have tried shielded pattern along with the circuit below the inductor? If I remember correctly, right, TSM 65 nanometer has M4, M5, M6 available for shielded option. I have not tried the shielded option. I mean, I would think that if you put the shielding at for M4, M5, or even M6, depending on the back end you might have you definitely have a capacitance, right? I mean, you definitely, so So usually the pattern ground shield that you want to have is definitely the bottommost. So of course, a lot of times if you have, the advantage of having an M4, M5, M6 shields is like you know that your ground is going to be really good. So we do that all the time for our transmission lines. You have a shield which are at the M3, M4, M5, whatever, that kind of thing. But for the inductor, definitely I've not tried. And again, I had this 65 nanometer digital CMOS, like the thinnest metal layers possible. So definitely not possible.
All right,
Okay.
guys, I think we'll have to call it there. We're already well over time. So let's thank everybody. Thank Amit for giving such an excellent talk. We had a very strong attendance today. We had 52 people online. So this is probably one of the best talks in terms of attendance, at least, that we have organized. So thank you very much, Amit.
Yeah, excellent job, Amit, and hope to see you again.
Sure. Thank you so much, Paul. Thank you so much, Utkarsh.
And thanks to everybody who attended. And I hope you found this as exciting and informative as I did. So if you're interested in attending more talks on LinkedIn, like I said, follow #MTTSCV, and we'll be coming up with the schedule for future talks shortly.
Sure.
So,
Thank you so much.
Utkarsh,
Yes.
I have one request, that those of the people who are listening, in case they are not IEEE members, I will strongly urge them to please become one. Thank you.
Yes, I did show links to membership links where you can go become IEEE member if you're not an IEEE member, or an MTT member if you're not an MTT member. So
great.
With that, we'll come to the end of the talk. And once again, thank you, everybody, and stay safe.
All right. Thank you, everyone.
All right.
Thank you.
All right. Thanks. Bye-bye.
Okay, bye-bye.